Log on, tune in, find out. Another good idea from Cambridge.
Sure, I'll just use it as a note taker. Okay. Can you hear me at the back?
I can barely hear you, like halfway in the middle.
Oh,
It's off.
maybe it's off. It's on. So my voice is low typically. If you have any issues, just remind me.
If you're ready, the guy there is Amihay Hanany from Imperial, and he will talk about Trivertices and hyperKahler manifolds.
Okay, thank you. So
I keep forgetting that, okay? I'm just the rudest.
Hurry up.
okay, so I'm going to talk about a class of hyperKahler manifolds. And so I'm a physicist in origin doing research in string theory, and this class of hyperKahler manifolds arise in string theory, and I'd like to show you why, or give you some motivation why this special class is. So I'm going to talk about a particular class. And I'm going to argue why these are interesting manifolds which deserve further study. Now, we're going to look at quivers. So the construction of these manifolds is going to use hyperKahler quotient. And then we will, typically this is done by quivers, but we will need to generalize the notion of a quiver, so that's another motivation for this talk. We will have to generalize this to something which is, which I call Trivertices. And we will see how this comes about. Once we will do this generalization, it will allow for a large class of hyperKahler manifolds that we can construct using this. Now, so let me start by some simple things. And the previous two talks were mentioning the McKay quiver. So let me start by the McKay quiver. And oh, this doesn't go up. Okay, so the McKay quiver, I have a collection of nodes, and I'm going to write down the equations for hyperKahler quotients. We are using a notation in physics which is perhaps slightly different than what is typically used. So I'll just introduce a notation so that we will be together on this. So what I'll do is that we'll give ranks to every point. And I'm going to take a line like that and assign to it two arrows in this way. So the nodes will be the same, and 1 and then 2. And I'll put some loops like that. And let's call this arrow by Q, and this arrow by Q tilde. So I'm going to take this to be N2, well, let's call this N1 by N2 matrices. And with complex entries, and those are going to be n2 by n1 matrices with complex entries. And there's going to be the hyperKahler quotient is given by a set of moment map relations. Which are conveniently given in terms of a superpotential. And let me write down these relations. So for every line, I'm going to draw, to write down a function, which is, well, let me put, let's call this phi 2 and phi 1, these arrows over here. And phi 1 is an n by n, n1 by n1 matrix, and this is an n2 by n2 matrix. And I'm going to write a function which is trace q phi 2 minus q times q tilde minus trace q tilde phi 1 q. Okay, and I'm going to sum over all such lines. So in a given quiver, the superpotential is going to be sum on contributions for all of these lines. Okay, now the relations are going to be given by derivatives of the superpotential, critical points of the superpotential. And the space that I'm going to consider are, before that, we're going to introduce an action. So there is a GLN action. For each node, I will have a GLN action. And that would take a field Q to G1 Q G2 minus 1, where so G1 is in as GLN 1, where and G2 is in GLN 2. Okay, so what I'm going to do is to look at the relations, the moduli space is the set generated by all Q's and Q tildes invariant under the GLN I actions and subject to the equations, the relations from the superpotential. Okay, so this is the object of interest.
Deliberately not including the phi's?
Sorry, what?
You said the phi's equal 0?
Yeah, so I'm not going to consider the phi's. They have a very interesting dynamics, physics of their own, but I'm not going to consider them. So so the moduli space in general is going to be a collection of several disconnected components, and I'm going to concentrate on the component which is just generated by the Q's. Okay, any other questions?
So if you set the phi's equal to 0, it seems like it fills that relation?
Well, I just take them, so first I take the relations and then I set the phi. So since the terms are linear in phi's, I'll get relations for Q's. Okay. Now there are several interesting. Okay, so several.
So what do you mean by invariant? You mean take the solutions and divide by the product of GLN, so you really want the invariant?
invariants under this action.
You want the invariant ones.
Yes.
It means the obvious.
Okay. Okay. So now let's see several examples. So that's the Cohen-Hammer Nakajima construction. So if you have rank 1, then I'm going to get C2 mod Zn, where n is the number of points over here. And what I'm going to consider is an interesting case where all of the ranks are 2. So in general, if these are k, all of them, then I'm going to be to get some symmetric product Sk of C2 mod Zn, or the Hilbert scheme of k points on C2 mod Zn. But I want to generalize this in several respects. So the first thing is that I'm going to divide not by GLN, but by SLN. Okay? So replace so the dimension of this moduli space is going to increase by n minus 1. N minus 1, where n is the number of points. And the minus 1 comes from an overall trivial action of the an overall C star. Okay? So, and then one other comment is that when I'm writing dimensions, I count in units of 4. So these are quaternionic dimensions. So this is going to be, the complex dimension is going to go by 2n minus 2.
I think you better, if the ends in the bottom line were k's. The ends are the k's.
Oh, sorry, yeah. And k over here. Thank you. Did I put k someplace else over here? And there was a k. Okay. Hope it's clear. Okay. Now there is one interesting property. If we set all k's to be 2, then we're going to have this quiver. And there is a property that the two-dimensional representation of SL2 is self-conjugate. Whereas for any other representation higher than 2, it's not correct anymore. There are two inequivalent representations of dimension n. So this property is very crucial, because then I can, then Q and Q tilde are the same objects. And therefore, I can write them as, both as a doublet of an additional SL2. Okay? So that's crucial. And this crucial property allows us to get the generalization of the quiver. Now, from the point of view of physics, it's more convenient to replace the objects, to exchange their notions. So let's exchange lines by vertices. Okay? So if I'll have two nodes and a line connecting between them, what I'll do, and also I restrict to the case that the ranks are 2, what I'll do is to replace a line by a node and the node by a line. Okay? But because, so here's an SL2, here's another SL2, but because this line corresponds to two identical objects, there is a third SL2. So now my objects, my basic objects, are looking like tri-fundamentals. So I have 8 complex entries. Which transform as a doublet cubed of SL2 cubed. And that's the crucial property. With this, I'm going to generalize to a very large class of models.
You're just telling us to do this.
Yeah,
Kind
it's
of
a
almost said it like you've derived it.
it's a construction. From my perspective, it's just a construction, and it gives you a general way of constructing many hyperKahler manifolds.
But when you said these two are the same, so obviously we produce a third.
Yeah.
Did we understand? Were we meant to understand that?
Well, I can tell you what we would say in physics. All objects that arise from these constructions will transform nicely under this third SL2. Okay. So if I want to count holomorphic functions, they will carry nice representations under this SL2. I don't know if this helps.
You're putting two 2x2 matrices together to make a cube.
Yes.
2x2x2 cube, and then saying it acts.
Yes, so now it's going to look like a 3 tensor, tensor with 3 indices. It has 8 complex entries, and so instead of calling them Q and Q tilde, I'm going to call them Q, alpha, beta, and gamma, and each of these indices has 2 values, 1 and 2, and there are 8 of them. Okay? But that's nice. How do I denote now the quiver? The Mackay quiver in this notation is going to look like this. Okay? What's the dimension of this quiver, of the corresponding space? So I can write down a set of moment map equations, just like I did before, and I can compute the dimension. The dimension is going to be 2. That's just, so I'm taking the dimension of C2 mod Zn to be 1, and then 2 copies of it will give me dimension 2, and I have an additional n minus 1. Okay, so the quaternionic dimension of this space is going to be n plus 1 dimension, so it's a hyperKahler manifold of dimension n plus 1. And let me write down the, let's look how this acts on the superpotential. So the superpotential is going to be defined as a sum over all vertices. And there's going to be a contribution for each vertex. So let's look at a contribution of this type. So here's a vertex, and it has 3 lines to it. Okay. The contribution, the superpotential is still going to be cubic, as we wrote up there. Okay. And so Wi, where I runs over the vertices, Wi is going to look like Q. So I'm going to denote this by Qi. It's going to have indices alpha, beta, and gamma. As we saw there, I should have 2 copies of them, 2 Qs. So let me put another Q. And let me put indices alpha prime, beta prime, gamma prime. Okay. Now I remember that each node in this quiver corresponds to a diagonal matrix phi. Now we have that each line here has a diagonal matrix, a 2 by 2 matrix. So phi 1, phi 2, phi 3. Okay, 2 by 2. So I'm going to denote them by 2 indices. So, and let's say we contract the first 2, alpha, alpha prime. And the betas and the gammas I'll contract with an epsilon. Okay, where epsilon is just a 2 by 2 matrix of numbers 1, 0, 0, and minus 1. Okay, and I'm going. So this is going to be for phi 1, and I'm going to have similar contributions for the other 2. So because this, the way I drew it over here, it's completely symmetric with respect to the phi's. So plus phi 2, beta, beta prime, epsilon alpha, alpha prime, epsilon gamma, gamma prime, and plus phi 3, gamma, gamma prime, epsilon alpha, alpha prime, epsilon beta, beta prime. Okay? Close the bracket. So I'm going to sum over all such contributions. Okay? Now, as we said over there.
Are you saying this Wi is equal to the previous Wi?
Yes. That's right. Yeah. Yeah. Okay. So, so here's my formulation. Let me just make it general now. So I have a graph with the 2 objects, lines, and trivalent nodes.
Sorry, I mean the thing before, it didn't depend in any way on phi 3.
Sorry, that's superpotential?
Yeah.
Yeah, phi 1 and phi 2.
Yeah, and the thing you've written now has a phi 3 in it.
Yeah, right. So in this case, so if so there are these are called the formations. So if you set, let's say, phi 3 to 0, you'll recover this one. Okay.
There was a term there for each line. There was one of these phi 2 minus phi 1 terms, is there? So now, and the whole superpotential is the sum of terms of this form.
Yeah, but he's borrowed. I mean, he has a point that we will have 2 types of lines. Those which are finite and those which are infinite. Okay, so a generic graph will look like Right, so here's an example. So I have finite lines, and I have infinite lines. Okay, so I can choose, for simplicity, the case where all of the phi's for the infinite lines to be 0. So there will be no relations coming from them. And there will be relations just from the finite lines. Okay, so the superpotential that we wrote down would just contain the finite lines, contribution from finite lines. In physics, there's certainly a room to add another term, which would look like mq tilde q. These are called mass terms.
So, I mean, you're going to take derivatives and then set the rest of the phi's equal to 0
Right.
anyway, right?
That's right, yeah.
So you could just write those relations, since it's linear in the phi's, you could just say the relations at the end of the day or whatever sits in front of those linear phi's on their own.
Right, so I'll take relations from those. And no relations from those. Okay, I'm also going to take invariance with respect to those. And I'm going to take any representation with respect to those. Okay, so it's going to be, geometrically, it's going to, these infinite lines are going to correspond to isometries of any metric that I would write on this hyperKahler manifold. So any metric on this hyperKahler manifold is going to be symmetric under those SL2s. And that's the bonus that we get. So the bonus that we get is that those hyperKahler manifolds are special because they have an additional symmetry that is not typically the symmetry of hyperKahler manifold. In some sense, it's a generalization of the notion of toric geometry. So in toric geometry, you have a torus collection of C stars over a base. And now what I do is to replace the C star by a non-abelian group, an SL2. Any questions? Okay, so let's formulate this. So I have graph with two objects, lines and trivalent nodes, two types of lines. And let's assign to each line an SL2 with an action as this action. And for every trivalent node, a term in superpotential. Okay, which gives me the collection of relations. And again, I'm interested in the moduli space, which is the moduli space of invariance with respect to the SL2 actions, and subject to the relations coming from the superpotential.
You're imposing some sort of dimension vector before writing down this action?
The dimension vector, I believe what you mean is just I take all of them to be SL2s. Okay, so let's see simple examples. Okay, the simplest example we can think of are this one. So let me write examples. So this is the simplest example one can think of. No SL2, so there are three SL2s which are infinite, and no finite. So that means that we are not imposing any invariance with respect to SL2. We are going to express all functions are going to be in representations of these three SL2s. Okay. Another thing that we do in order to make this more slightly more explicit, we can compute the Hilbert series. And here, because there are no, there's just a collection of 8 objects. We're just going to get C8, and that's it. There's no, the moduli space is very simple in this case, C8. And the Hilbert series is going to look like 1 minus t to the power 8. Okay, so it's going to be a function of one variable.
What are you calling the Hilbert series?
So it counts holomorphic functions on this space, right? So in this case, I'll have a single object Q, okay? And I want to count how many functions there are for a given degree, right? So in degree 1, 1Q will be 8 objects. In degree 2, I'll have 9 choose 2, okay? But I can also refine this function to include the weights under these SL2s.
Wasn't there an SL2 that we were going to divide by?
Not for this case. When we were discussing this example, yes. So whenever there are finite lines, we will divide by SL2s. Whenever there are infinite lines, we are going to keep the symmetry. We won't impose two invariants. Okay, so let's define the Hilbert series. And now it's going to be a function of several variables, t, x1, x2, and x3. And those x's, they count weights under each SU2. SL2. Okay? I have 3 of them, and therefore I'm going to have 3 variables, 1 per each SL2. Okay? So it's fairly easy to do that, since this space is just a collection of, it's a flat space. So I'm just going to put x's by just imposing the 2-dimensional representation for all of these 8. So it's going to look like product epsilon I equals to plus minus 1, 1 minus t, x1 to the epsilon 1, x2 to the epsilon 2, x3 to the epsilon 3. Okay? Now, this admits an expansion into characters of SU2 cubed. So I'll just write it as generic expansion. These are characters of SU2 cubed, of SL2 cubed. Okay? For example, the first one, the order t, the coefficient of t is just going to be chi1 of x1 times chi1 of x2, chi1 of x3 times t. So this is equal to 1 plus this plus higher orders in t. And this is nothing but telling me that the first few objects are just the product of the 2-dimensional, 2-dimensional, 2-dimensional. Well, chi1 of x is x plus 1 over x. Okay? Question? So now my question is whether I can write down the Hilbert series for the whole class. Let's see a few more examples. Let's take this model. Okay? It has one finite line, one infinite line, and one vertex. Okay? So there's going to be one SL2 action that I'm going to take invariance with respect to. That's this finite line. There's going to be one SL2 for which I'm going to characterize all holomorphic functions as representations of it. And this one vertex tells me that I need to start with C8 and impose the relations on the SL2. I need to impose both the relations from the superpotential and to impose invariance. Okay? In general,
I mean, it's really fair to say this superpotential relations are just the moment map relations for the action of the
That's
SL2s
right.
you want to act.
that's right, yes.
Superpotential is a red herring, really.
Yeah, that's right.
People who know what moment map relations are.
Yeah, so I can, instead of talking about the superpotential, I can say I have an SL2 action, SL2 valued moment map relations per each finite line. And I can, and for each infinite line, I'm going to leave the states as they are. Okay, so if this is more, if this is clear, if this is a better language, then certainly, yeah. Okay.
Excuse me. But can you always turn this back into the original quiver problem? I mean, can you dualize your graph again?
Very good question. I can do that for 0 loops and for 1 loops, but not for more. Okay, let's see. So here's an example with one loop and 2 external lines.
Before you do an example, are you going to tell us the geometry here? Shouldn't this be right for a public schema 2 points?
This is fairly simple, and that's
Symmetric.
yeah. Oh,
So you take affine quotients and imposing the stability conditions. I mean, that thing right there is like the symmetric product of 2 points on C.
So for the problem he's interested in, it doesn't matter.
Sorry?
If each wants the Hilbert series, it doesn't make a difference.
Okay, yeah, that's right.
Okay. The discussion. With okay. For here, it's slightly more. I wouldn't know how to tell you this space. I can write down the Hilbert series, but from this to extract the set of equation generators and relations will take some more work. But here are 2 examples. This is the McKay quiver. So I have this formulation for quite some time, but this is new. Okay, so Balázs, for your question, this one I don't know how to construct using the previous formulation. Okay, and now I'm going to argue that they have the same moduli space. Okay, which is non-trivial. Those are 2 inequivalent hyperKahler quotients, but they give the same moduli space. Here's another example. This corresponds to the non-affine quiver, to the Dinkin. Let me just write it like that. 2, 2, 2, 2, and 2, like that. Okay, now let me count. here there are 3, so maybe I should add one more. So then this one will correspond to this one. Okay? So if there is a loop, if there is a single loop like here, then that's the affine quiver. If there are no loops at all, then I'm going to get the non-affine quiver. But with this new formulation, I can get a few more. I can get 2 loops. So here's one model, for example. So there are 3 SL2s. All of them are finite lines, and therefore I have to divide by all of them. And that's something I cannot get, Balázs, from, so this one I cannot get from the previous formulation. Any graph which will contain more than one loop, I don't know how to construct using the previous formulation. So that's the advantage of this notation.
So does this equivalence over here is like a WDDD, does that apply to sort of any graph? I mean, could you make that part of a much bigger graph and have the same equivalence?
In what?
Well, you've turned you've turned.
Oh yeah, so
you've done WDVV, right?
So there are sewing relations or gluing relations that I can think of, right? So here's an example. So gluing relations. Suppose that I have a space with E1 external lines and G1 loops. And here I have another space with G2 loops and E1 lines, external. These are external. I can perform a process of gluing, and then I'll get a new graph with G1 plus G2 loops and E1 minus plus E2 minus 2 external lines. Okay. So by this, I'll start with a hyperKahler manifold over here, another hyperKahler manifold, and I can combine the 2 manifolds using this prescription. Let's look at the dimension. So the dimension of this moduli space is E plus 1, okay, independent of G. And I have, there is a small computation which shows how to compute this dimension. I won't do it.
In your example, you had the same moduli space. Will you always have the same moduli space if you contract internal edges, or transition
like
through such a contraction? Your sort of your finite edge. If you contract it and
I see.
going, you get that other picture.
Right. So there's going to be a transition which take, let's say, this graph and exchange it with this graph.
Mm-hmm.
That's what you have in mind, right? And so, yeah, so to move from this one to this one, I need to go through this transition. And the claim would be that the moduli space is invariant under such.
And you can do that locally in any graph.
Yes, right. Yeah. So any number of successive iterations of this type will keep the same moduli space. So that's a very nice property. It means that the moduli space depends on G and E, but not on the detailed structure or the details of how they connect. The lines connect. Okay? So I can think of, if I fix the number of G and E, then I can think of many ways of having such graphs. Each of them will correspond to a different hyperKahler quotient, but all of them will give the same moduli space.
Are you saying that, I mean, assume I name the external edges and I name the SL2 actions of them?
Yeah.
Are you saying that statement sort of, for instance, the representation of those SL2 on the Hilbert series, that's the same also, or just, the state
Yes,
abstract?
right. So the Hilbert series is going to depend on G and E only, and not on the particular details of how I connect the lines.
That's not the question. Is the Hilbert series as a character of the external SL?
Yeah.
The answer is yes. Claims yes.
What's the dimension?
The dimension is E plus 1. Okay. I just need to count the. I need to count the number of vertices. So the number of vertices is 2G minus 2 plus E, the Euler character if this was a Riemann surface. And the number of lines of finite lines is 3G minus 3 plus E. Okay? So I need to count how many vertices there are, and I need to remove a moment map per each finite line. I need to remove 3 of them. And after I do this computation, I'll get the dimension, which is E plus 1. There's a slight subtlety here, because for every loop there is an addition. There is an action which is not. There is a C star which I do not divide by, but I can show it later. Okay, so where do we stand at this point? Let me write a general expression for the Hilbert series, and what I'd like to do is to take this function over there, up there, and to be able to generalize it to any G and any E. Okay, so written in this form, it's not the right way to generalize. It doesn't look like the right way. So instead, what I need to do is to perform an expansion. So I think this is what we found by trial and error. So if I write it as an expansion, over a collection of characters, and now this becomes a formula. Let me write just the general formula. So I'm going to define a function Fm of x to be some n from 0 to infinity. And here I'll put chi 2n plus m of x, t to the 2n. And chi n of x is sum m from minus n over 2 to n over 2 x to the 2n. Okay. And then the Hilbert series is going to be, and now it's going to be a function of all xi's. Takes the form 1 over 1 minus t to the 4th, sum m from 0 to infinity, t to the chi m, product I from 1 to e. So this goes over all finite lines, all infinite lines, fm of t and xi. Okay? And then there's going to be another contribution, 2 to the chi m plus chi plus 2, product I from 1 to e, fm plus 1 of t and xi. Okay, so slightly long but relatively simple formula. Well, chi, I should say what chi is. Chi is just this number. Okay, so that's the general expression. And now what I can check on this is that this expression is invariant under this gluing operation. Okay, what I need to do is to take one of these SU2s, sorry, one of these xi's, I need to integrate over it. So that will amount to an integral formula, some contour integral with respect to the x, to the corresponding x. And after performing the right integration, I'll start with G1 and E1, G2 and E2, and end up with this expression. So this formula is consistent with this gluing relation. Okay. Now I can do several things. I can, for example, add external legs. For example, so let's use the gluing. So I have gluing. I can take a surface with G loops and E legs and add to it the basic vertex, which is this, the simplest one. So by the formula that we have over there, what I do is keep the same number of loops but increase the number of lines by 1. So this is G equals to 0 and E equals to 3. I add them together, and by this I get the G and E plus 1. So I can write some recursion relations according to these, what you said, WDVV equations. A special subclass is to take any G and no external lines. The dimension of this hyperKahler space is going to be 1 quaternionic. And in fact, there's classification of all such things. These are non-compact, so it can only be one of ADE classification. And so the moduli space is going to be C2 mod D G plus 1. Okay? The graph can look like this. So we saw there the case of G equals to 2 and equals to 0. So let me draw it again. or I can draw a different hyperKahler quotient, this one. Both of them will have the same moduli space. Or in general, I can take these with G loops, or make them look like this. So here's one with G equals to 3. Okay. Another special subclass is any G equals to 1. The dimension is going to be 2, and it is a complete intersection generated by 5 generators with one relation. Okay, so the Hilbert series in this case is quite easy to write down. It's just going to look like a simple rational function. Okay, let me summarize. Are there any questions?
Yeah, what was that DG plus 1? It's just the
Sorry?
It's just the AD group of D type, or?
That's right, yeah. So this is a C2 mod gamma, where gamma is the corresponding dihedral group.
Binary type.
Sorry?
Binary type.
Binary dihedral, yes. Any other questions? So let's see if I said all the comments I wanted to say. Okay, so let me just emphasize that the special property of these hyperKahler manifolds is that they have an additional product of SL2 symmetries, a property which is not required for a generic hyperKahler manifold. So this is a special subclass of hyperKahler manifolds that are symmetric, and they have high amount of symmetry because the symmetry is related to the dimension. I have a dimension which is E plus 1, and the symmetry is SL2 to the power E, almost the dimension. Right? So there is an additional SL2 that acts on the complex structures, but this SL2 to the E is a bonus symmetry, which is not there.
Does it truly depend on G?
G roughly, so I can only say that from this example, G roughly counts the degree of singularity. So it tells you how singular it is. I don't know what are those spaces for higher E, because unfortunately there's no classification for the hyperKahler manifolds which have dimension higher than 1. So I haven't seen this in the literature. I mean, if anyone knows something which looks similar to this, I'll be happy to know. I've been asking this question for quite some time. But so roughly, the way I understand the meaning of G is that it counts the order of the singularity. So E counts the dimension, and G the order of the singularity.
So these aren't manifolds, and you don't even know whether there is a Crepant resolution, for example? Or?
Since I divide by SL2 and not by GL2, there's no natural parameter which will give the resolution. Even though we know that for this, there are G plus 1 different deformation parameters, but they are not obvious in this formulation. In the physics, this will correspond to some kind of a non-commutative deformation of the particular field theory, something which is not an ordinary field theory. But I don't know much about this. Now, for higher cases, it's just, I mean, the fact that you're dividing by SL2 as opposed to GL2 really makes the difference. Any other questions?
So I guess you mentioned that you don't have a product expansion of this general Hilbert series. If you set the x's all equal to 1, so you don't care about the representation, can you get a product expansion then? Is that
Haven't tried. You just get a collection of dimensions. You see, this one looks like, so this will look like a simple rational function. And here, there will be a sum. So it's a sum over rational functions. Perhaps it's possible to sum it. Probably not. Probably it's, as G and E grow, it will become more and more. I don't know. I mean, maybe I should ask you for.
And the proof of that formula is just that you know it like on the triangle and on the punctured torus or something, and then
so that's
it satisfies the gluing.
So now I remind you. Now this is the time that I should remind you that we are physicists. So we don't talk in terms of proofs. So we tried this formula for a few cases that we are able to perform the integrals. Now, in actual terms, the way to compute those Hilbert series, what you need to do is to write a contour integral per each line. And so you'll get a product of, where was this? Remember, the number of lines. Number of finite lines is equal to 3g minus 3 plus e. So this is the number of integrals of contour integrals that I need to perform in order to get this function. And so this I can do for sufficiently low values of g and e. Okay, but I can use this formula for any g and for any e, and this I can do. This we showed for any g and any e. So the details are in the paper. So you can have.
So the gluing and the transition, those are rigorous.
Yeah.
So what's wrong with the argument I just said to prove that?
That's right. I mean, if that would be nice.
You should point out when you say to mathematicians that physicists don't deal with proofs, that ancient Chinese mathematicians also dealt with checking enough cases until it became obviously true, and this is the tradition of mathematics.
Okay.
History.
Thank you. You see, what I can say is that, there's one point which is, I think it would be very nice to show, to prove that what I said, that the moduli space, or at least the Hilbert series, does not depend on the particular arrangement of lines, G and E, and only depends on the values of G and E. Okay. So for this, we have an explicit computation. We can compute this explicitly and this explicitly. Those are simple enough cases that we can compute. But as you grow with G and E, the number of possibilities grows exponentially. And so one needs to show that there is no dependence on that. So, or alternatively, to show that under those local transitions, which are here, the Hilbert series does not change, or the moduli space itself does not change.
Oh, so that's an observation. That's not something you showed.
Yeah, remember, I'm a physicist, yes.
But physically, it's clear that has to be the case, right?
You're also a physicist, yeah?
Yeah.
Yeah, I mean, if you want, I can give you one more hint. These are all the generations of Riemann surfaces of genus G and E external lines.
So it can only depend on the Riemann surface and the number of functions, not any way you triangulate it or decompose it or whatnot.
Right. So if you could consider this as a beginning of the proof, that's fine with me. Yeah.
What is it? You haven't at the moment written down anything which depends on a Riemann surface at all. Privately, you know.
The Hilbert series depends on only the two parameters, G and E, which was not obvious from the beginning. Okay? So by drawing the graphs, I cannot guarantee at all that the Hilbert series will only depend on just two integers. Okay? So this I consider to be a non-trivial fact. Well, not fact. Experimental observation. But then there is the you could also write the those moduli spaces as algebraic varieties, which is more than just writing the Hilbert series. And again, here the claim is that these algebraic varieties do not depend on the particular arrangement of the graph, but rather on just two variables, G and E. Okay, which is again non-trivial.
Does that mean if you wrote down a Riemann surface of genus G, any Riemann surface of genus G, and with E punctures or N's or whatever, you would expect to be able to write down some variety associated with that?
Yeah.
Which would be?
So I can tell you what it is for simple cases, right? For this case, I can tell you what it is. For the E equals 0 and any G, I can tell you. But for the general case, I can just, I mean, the most general statement I can make is about the computation of the Hilbert series. Any other questions?
Is it, you're not expecting it to be some moduli space of Higgs bundles on that Riemann surface with parabolic structure?
Well, in some sense, these are all moduli spaces of Higgs bundles. I mean, from a physics perspective, anything which is hyperKahler quotient is like that. But perhaps when you say Higgs bundles, we mean something else. I don't know. Oh. Anything which is just hyperKahler quotient. We call those Qs. We call those Higgs fields. So you'll have to explain to me what you mean by this, and then I'll be able to tell you what.
Well, but there's alcohol outside, so I should.
Okay, I guess I'm done. Thank you very much.